Welcome to episode 247 of the Engineering Career Coach podcast, the first podcast dedicated to helping engineers and technical professionals with both their personal and professional development. In this episode, I will be talking with Russell Dupuis, an electrical engineer and professor at the Georgia Institute of Technology, as well as the co-winner of this year's Queen Elizabeth Prize for Engineering, about the use of LED technology for state-of-the-art lighting in engineering and how LEDs have changed the world and will continue to do so. Now, I'm your host, Jeff Perry. I'm the new host of the Engineering Career Coach podcast. I'm a leadership and career coach that helps engineers and technical professionals realize their true potential. I love helping people make intentional career transitions and optimize their success. Often we work on developing soft skills like leadership and mindset to unlock their hidden potential and remove self-imposed roadblocks. I founded More Than Engineering to bring together my love for engineering and technology with my passion for helping people improve and live more fulfilled lives. And I now run a program called the Engineering Career Accelerator. You can find more information at engineeringcareeraccelerator.com. Now, let me tell you a little bit more about our guest for today. Professor Russell D. Dupuis is an internationally recognized expert in compound semiconductor epitaxial materials and devices, including optoelectronic and electronic devices. He worked in industry at Texas Instruments and Rockwell International. He was a member of technical staff and a distinguished member of technical staff in the Physics Research Division at Bell Laboratories in Murray Hill, New Jersey. Dr. Dupuis was appointed as a chaired professor in electrical and computer engineering at the University of Texas at Austin in 1989. He joined the Georgia Institute of Technology in 2003 as a full professor in electrical and computer engineering and material science, and became the newly established Steve W. Chaddock Endowed Chair in Electro-Optics and a Georgia Research Alliance Eminent Scholar. He has won many national and international awards for his work on compound semiconductors. Now, let me bring you into our main segment with a quote that is applicable to today's topic. This quote is from Bill Gates, the founder of Microsoft. The advance of technology is based on making it fit in so that you don't really even notice it. So it's part of everyday life. Now let's transition to the main segment of today's show. Now it's time to jump right into the main segment of our episode. Today, I'm talking with Professor Russell Dupuis, and we'll be talking about LED technology. Professor, welcome to the Engineering Career Coach podcast.
Thank you very much. I look forward to this.
Yeah, and I'm excited for this discussion. Now, before we really jump into the topic, can you tell us a little bit about what got you interested in engineering as a career, and how did you decide to become specifically an electrical engineer?
Well, I was always interested in the world writ large. I was from a farm in Illinois, so we're always tinkering with something. And my parents were quite interested in improving their equipment, improving their farming. And my mother was a teacher, a second grade teacher. So she was interested in education. And I was good at math and science, and then in high school, physics and chemistry and biology. So I was lucky to have a friend who was ahead of me in high school, who had attended the University of Illinois in Urbana-Champaign in electrical engineering. It turns out his father was an electrician, so he chose electrical engineering. And from what he was telling me, it sounded interesting. It sounded like exciting kind of work to be involved in. So I applied for electrical engineering at the University of Illinois in Urbana. So that's sort of the basis, almost by accident, but not quite. It was, do you want to do mechanical engineering and sort of worry about, I'm going to say this, people will object maybe, but gears and levers? And or do you want to follow electrons around? So I thought, electrons sound interesting. They do a lot of different things. So with the interest in physics, I was focusing more on electrical engineering.
Okay, very cool. So that mix of the background and the interest and just the people in your life kind of led you through things, and certainly you've grown and developed and blossomed in your career over time as well. So sometimes we can take these hints, but also just kind of run with the opportunities that are given to us for sure. So Russell, some of the work that you do, or a lot of the work that you do, as I understand it, really focuses on LED lighting. And recently, the technology and your involvement in it won this Queen Elizabeth Prize for Engineering. And this is one of the world's most prestigious engineering prizes because of its benefit to humanity and its impact on the environment. So can you talk to us and help us understand a little bit more what the benefits to humanity the LED provides, and how does it also help with things like climate change that we may not be aware of?
Well, that's a very interesting and broad topic. LEDs are not really new. They have been studied for many years. In fact, 1907 was the first report of light emission from a semiconductor by a British engineer whose name was Round. But he didn't understand the physics. He didn't understand the material. So it was like a one-page report in a journal, and that's where it ended. And then in the 40s, physics entered the quantum mechanical age for solid state materials, and people started to understand what these strange things called semiconductors were. And as a result of that, the transistor was invented in 1947 by John Bardeen and Walter Brattain at Bell Laboratories in New Jersey. And that brought forth a lot of interest immediately because it was such a dramatic improvement in potential improvement, at least in performance and reliability. And that created a dramatic interest in semiconductors that expanded. And then in the 1960s, people started to develop other semiconductors that were from column 3 and column 5 in the periodic table, like gallium arsenide, for example, and eventually discovered that these materials were really good at emitting light. Only it was all infrared light. So no one had a good visible light emitter from semiconductors until my PhD advisor, Professor Nick Holonyak Jr., working at General Electric in Syracuse, discovered and invented a way to make 3-element semiconductors that he could engineer. He was an electrical engineer, but was seeking to improve a device he was working on. And his idea was, I can't make what I want with what Mother Nature has given us so far, so I'm going to help her a little bit and make something new. So suddenly you have an electrical engineer who's interested in materials and creates the 3-element semiconductor for the first time in the history of the known universe. And that allowed him to make red light emitting diodes, the first visible, at least direct band gap visible light emitting diodes. And from that, he made the first visible laser diode in 1962. So suddenly in 1962, you have lasers in gallium arsenide, lasers in gallium arsenide phosphide emitting in the red. And it became clear that that's pretty dramatic. You have a semiconductor emitting coherent light. What about making light emitting diodes of various colors? And again, that was a challenge because no one understood all of these materials very well. But in 1963, there was a Reader's Digest article published about the gallium arsenide laser diode and the gallium arsenide phosphide laser diode. And they interviewed my advisor, who was, again, at General Electric then, and he predicted that semiconductors would be the ultimate lamp, that no process known to humans at the time, at least, would be more efficient in creating light from current. And the article, it went on to say, well, eventually we could have televisions as thin as 1 inch and automobile headlights made of semiconductors, and this just basically going crazy with applications. And those weren't Nick's predictions. The writer of the article took what Nick told him and said, "Oh, we can make headlights," and that was pretty bizarre because no one knew how to make white LEDs at the time. It had just had sort of red ones, kind of dim red ones at that. So it took a long time from 1962 to about the middle of the 80s before really high efficiency LEDs were available commercially. A lot of development here in the US, in Japan, in Europe in particular, that created these new types of devices. And Professor Holniak also invented the 4-element semiconductor. So it turns out that today, if you turn on anything practically that has an indicator light, it's probably a blue indicator light or a white one. And those all use 3 or 4-element semiconductors. Those use his innovation. Unfortunately, never patented that concept, so he missed out. At any rate, today we have a wide variety of high efficiency LEDs. Most people know the green traffic signal, the yellow traffic signal, the red traffic signal, the red taillights on their cars, the white LED headlights on their cars, the heads-up displays, the computer displays, the iPhone displays. All of those came out of this concept from 1960s of a ternary, and then in the 70s, the quaternary 4-element semiconductor. And a lot of hard work and materials development that supported all of those ideas and allowed us to get where we are today.
Wow. So certainly a lot of applications that seemed kind of far-fetched in a long run back in the 60s when this technology was just barely starting to emerge. But sounds like pretty much all of those have come true as we see, right. And just look around and what the technologies that you and I are looking at as we talk right now. I mean, we are living and breathing that. But so let's get a little bit further into this. And some of the other applications and long-range impacts of this. So when we talk about the impact of humanity, certainly in the applications and the technologies we're able to do as far as productivity and access and things, but talk about some of the big problems we face as far as climate change and stuff like that. Where are the impacts that just continue on beyond just the technology that we hold in our hands?
A very good point. In fact, that's really the big impact of LEDs in terms of the economy and health of the world. Obviously, it's convenient to have a highly efficient LED in your cell phone or the backlight your computer screen, but that doesn't save the world very much. So the fact that light emitting diodes are so energy efficient has caused them to be adopted and adapted almost universally across the planet for lighting applications of all kinds, including signage, including interior lighting in homes, in businesses, in parking garages, in streetlights. And while the impact has been estimated by various people, it's really trillions of kilowatts that probably have been saved by now. And several years ago, the DOE was projecting that you could save 100 large power plants if LEDs were widely adopted by the 2050 timeframe. So you would imagine that even with that sort of outlandish kind of timeframe, there could be a big impact on carbon emission as long as people don't waste light. Actually, this is one of the problems that lighting has become so efficient and so effective that often some of it gets wasted. And that's another advantage to LEDs. If you design your fixtures properly, particularly for outdoor applications, you can very efficiently use the light that you're generating much more efficiently than, for example, sodium lights. And you even see that in cars now because they have smart headlights that direct the light where it is needed and not where it's not needed. So much more efficient use of lighting is important. And then there's the even more dramatic change you can bring to people in sort of remote areas or in poor areas where they don't have access to the power grid. In many parts of India and Ceylon and Sri Lanka, power is really expensive. And so a simple solar panel outside and a few batteries and an LED lighting inside allows students to study at night, to cook with lighting. Even I learned this recently on some small fishing boats. They used to have kerosene lamps, which were very dangerous for night. And now they've got battery powered LEDs and much more light and much more safe to have on board a ship or a small boat. So I think everybody who thinks about this problem realizes that LED lighting is a big positive impact on humans on Earth, but they may not realize it has a big positive impact for humans off Earth. So, for example, in the space station, the ISS, they have lighting that it follows the circadian rhythm of living on Earth. So the color temperature changes with time. So it simulates a day where the morning light is different than the noon, different than the evening light. And that helps regulate their biological clocks, helps them sleep better, helps them be more efficient. And that's obviously affecting a few humans, but if we get smart lighting systems like that in hospitals and in care facilities and even in workplaces, it could improve efficiency of humans and the health of humans. And then there's another interesting thing, being from a farm originally, is the lighting for growing plants. And so I call it artificial agriculture, where either inside buildings or even in remote places, you might be able to improve the use of nutrients to grow plants, might make it much more efficient to take the fertilizer and the material you're adding to the water or the soil and produce food. Many of us have seen the movie Martian, where you got to grow a bunch of potatoes, and that would be easily done. In fact, I think Matt Damon did that with LED lighting. So as we venture from Earth to Mars, and Mr. Musk brings us along on his ride, we might want to have LED lighting inside the vehicle and growing things on the way and growing things when we get to Mars. And the sun is much less strength back there on Mars, but still could generate solar panels, solar powered energy, and use that more efficiently in a confined space to grow food. So I think it'll be not only on Earth, but off Earth. It's already off Earth in the ISS, but eventually colonies on the moon or certainly on Mars would probably benefit from this technology.
Wow, the benefits and the applications continue to go farther and wider, and probably some applications that we don't even see now that 10, 20, 30 plus years down the road will just continue to be discovered, right? And that's one of the great things about science. You know, we get to keep discovering.
One of the newer applications being developed now, in fact, is for LEDs in the ultraviolet to be used to kill bacteria, especially important in COVID times. So we're moving from visible to higher energy photons in the ultraviolet around 260 nanometers to kill bacteria and other pathogens. So for water purification, for air purification, for surface decontamination, it's possible we'll have large banks of these LEDs in municipal water plants, because it's going to take a few years, but eventually we'll have really efficient ultraviolet LEDs, more efficient than what's being used today in municipal water plants.
Yeah, so can you talk to us a little bit more about that journey that the technology has been on? You talked earlier about kind of how it was discovered and kind of been through these different phases, but it, like you said earlier, the one of the great importance things about LED technology is its efficiency. But things have certainly become more efficient since its discovery, by orders of magnitude, and will continue to be so in plenty of these other applications, like you're talking about, like using for UV applications for purification and other things. So would you mind telling us a little bit about how we moved through these various phases from, just having these dull red LEDs to, really increasing the efficiencies and the applications here as the technology's progressed?
I'll try. Surely, as I mentioned, that one of the door openings that happened was when Professor Olniak invented the three-element semiconductor and then the four-element semiconductor. And that opened a whole wide palette of materials that could be used for LEDs.
Mhm.
And then the question is, well, how do we make these? How do we produce this material? How do we take those four elements and combine them and make high quality materials? How do we process them? How do we get the light out? Because light bounces around inside these materials. You have to develop concepts, engineer concepts for light extraction.
Mm.
So there's something called the internal quantum efficiency that we have to optimize, and then the external quantum efficiency, and then there's the power efficiency. So lots of variables need to be co-optimized, but it's all not too practical until you can make these materials by the square meter almost efficiently and cheaply. And that's been one of the big innovations along this path. Once we knew we could make 3 and then 4 element materials, the question became, well, how? How do we make these, and how do we take aluminum, gallium, indium, and phosphorus and combine them? How do we take aluminum, indium, gallium, and nitrogen and combine them? And I was fortunate to be able to help with that problem. In 1968, a chemist named Harold Manasevit, who was working at North American Rockwell at the time in Anaheim, California, invented a process based on chemistry he used in his Ph.D. dissertation. And that chemistry was eventually called metal organic chemical vapor deposition. It uses something called Lewis acids and bases, which I won't go into, but basically he developed a process that could grow semiconducting films like gallium arsenide on insulator substrates like sapphire. And so it was very challenging to understand that process and to optimize it. And what was more unfortunate is large lattice mismatch between single crystal sapphire, which is pure aluminum oxide, Al2O3, and gallium arsenide, for example. So the materials, while were interesting, they weren't very high quality. They were much lower quality than other technologies could make on gallium arsenide. But he was very focused on growing on insulators. He wanted to make semiconductors on insulators for a lot of reasons that were very good at the time. And little did he know that whole idea was the basis now for all of the blue and green and white LEDs we use today. They're all grown on sapphire. They're all grown on his concept, beginning around, he started this in 1967. And I started working on it a little later in 75 and said, well, why don't we try on single crystal substrates of semiconductors? And so I made the first laser diodes using this process, the first solar cells using this process. And these were infrared lasers, but clearly, if you wanted to change some atoms around, you can make visible ones. So today, every solar cell in space that we know of, it's operating right now. Certainly the current generation, for example, all the SpaceX's, every time they launch 60 satellites, those are all powered by cells made by this process, MOCVD, following work that I pioneered. Most of the cells at this International Space Station are of this kind as well, maybe all of them as far as I know. And so besides the LEDs, the solar cells technology is revolutionized by these same concepts and approaches. Eventually, as I said, the material systems expanded. So we have UV LEDs, blue LEDs, green LEDs, red, yellow, infrared LEDs. And so at this point, pretty much you can get any photon energy you want within limits, of course, but certainly visible, all the visible is covered by MOCVD materials.
Wow. How cool to see, that connection in the various pieces of that technology, from the production of the energy using the solar cells all the way through the use of the energy in LED lighting applications, in the connections with some of the same types of technologies that you're able to do. So any other pieces of this process? I'm kind of interested to learn more about some of your other contributions and your work over the years in this field, and certainly what led to what has recently been a part of this recent Queen Elizabeth Prize for Engineering, and some of the pieces that you've been involved in.
Well, my piece, if you will, if I can make that claim, is more about the application of the materials technology that I worked on and the innovations I provided in that space. And it's expanded into electronics, and so high frequency electronics, all of the electronic systems we count on today. As you probably know, the internet is connected with optical fibers across the planet, across the United States, across the oceans. So all of that work that went into optical engineering of those big systems is based on materials grown by MOCVD. And again, these same semiconductors, but in the infrared. So this LED award is really nice. And of course it impacts the energy equation very directly. But the internet and the fibers that are buried in the ocean are another feature of this. That imagine we had COVID and we didn't have Zoom, or we had no internet. We couldn't, Google Lady Gaga and see what she's up to. How would we entertain ourselves? Probably reading more books. Maybe that'd be good. But so there's another layer of this that is not LED related, but it certainly is improving people's lives. And when you think about potential telemedicine and taking care of diseases at a distance, and even psychological interventions at a distance, so those are immeasurable, value to humanity. Maybe not help our global warming issues, but it helps the livelihood and the probably security and safety of people too.
Okay. Excellent.
So
Well, thanks for sharing that the different aspects and your involvement in that. And obviously it's a team effort, and you've built upon the work of other people, like you talked about your advisor and some of the early work that he was able to do, and you've collaborated plenty of times over the years. I'd love to pick your brain here as we start to wrap up here on the principles of mentorship and learning from others. In your opinion, when we're talking to plenty of engineers here who are going to be listening to this, how important are mentorships and collaboration efforts in this field of engineering as we continue to move forward?
Well, I think they're critical. I was lucky to more or less wander to Urbana and join the electrical engineering department there. And then I was even luckier to take a class as a junior from Professor Holonyak, who was teaching a course on quantum electronics for juniors. And it was so interesting. Obviously, as a student, you have engineering drawing, you have calculus, you have all sorts of EMAG courses, but this one lit my fire, so to speak. And he was such a dynamic individual. And then, of course, he lived it all. He lived the history that he was teaching. And I had a senior level class from him because I liked so much. He had follow-on class, and I was fortunate to be a good student. And when I asked him about joining his lab for a Ph.D. or a master's degree, he said, sure. So I was lucky there was an opening in his group at the time I needed it, and he had funding. And so I started out even as an undergraduate research assistant in his lab. And we had a very productive time. I got my PhD in 3 years and continued to work on this area since that time. So it's really fortunate for me to have that experience. And Professor Holonyak has had 60 PhD students in his career.
Wow.
Many of them are leaders. And I was fortunate, as you may know, to win this award with Professor Holonyak and one of his other students, George Crawford, who was ahead of me. I didn't know George as a student. I only knew George after he had graduated. But so it's like the three amigos working together in various aspects of this problem. And then we have these good colleagues from Japan, Akasaki Sensei, who was the instrumental leader of taking MOCVD and growing gallium nitride semiconductors, and Shuji Nakamura, who contributed the further technology improvement and innovation and developed a ternary indium gallium nitride, which became the leading material for blue and green LEDs. So it's five friends really that are working together in some respect. But yeah, it's really nice to be with George and Nick in this award. It makes it even more special, but the Queen obviously makes it even super special.
Yeah, well, that's excellent. And congratulations again. This has been a pleasure to talk to you and learn from this. This has been a little bit more on the technical side of some of the other topics that we cover on this episode, but always tying it back to, no matter what we're working on, the technologies or the organizations or the research that the listeners are working on, finding that core of the mentorship and the innovation and how working and together and collaborating is really what makes it all happen in the end. So thanks for sharing that. At this time, we're going to transition into the Take Action Today segment, where we'll get a final takeaway from Dr. Dupuis before we end this episode. Now it's time for our Take Action Today segment of the show. We've learned so much from Dr. Dupuis about the advancements in history and applications of LED lighting. And Dr. Dupuis is going to share with us one more final takeaway that each of us can take with our adoption and the importance of LED lighting technology now and in the future.
So I think that the single most useful thing people could do is look carefully around their houses and their businesses and see if we can incorporate more LED lighting. Certainly in the home, that's an easy thing to do. But today you can replace a standard fluorescent light with LED lamps very easily. And so as people design new buildings for architects and exterior and interior lighting for new buildings, then that's obviously a prime place to put LED lighting. And as far as other things you can do is make sure that if you're designing fixtures, especially external fixtures, to focus the light where you need it and not let it go into outer space. There's a lot of light pollution. People are worried about light pollution because our astronomers are seeing a lot of extra light where they don't want it. So be careful when you're designing these things.
Okay, excellent. Well, thanks so much for all of the things you've been able to share today. Is there any other places or resources you would suggest for people who are interested in learning more about the history of the technology or some of the work that you're involved in that you would point people to if they were interested to learn any more?
There's a lot of really good information on the Department of Energy's website. So if you just Google on the DOE website, light emitting diode or LED, you'll find a lot of information about energy efficiency, how many nuclear power plants we wouldn't need if we had adopted lighting by 2050 or 2030. So there's lots of resources in that regard. There are many technical articles as well. I've written a few myself on LED history, and of course then we have the major industry associations. So there's a whole group of associations associated with the lighting industry that, again, the DOE website probably would have access to or links to.
Okay, well, excellent. Thanks so much for sharing, and look forward to seeing more adoptions and applications of this technology as we move forward. Thanks so much.
All right, thank you very much.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and questions. Go to www.engineeringmanagementinstitute.org, where you will find a summary of the key points discussed in today's episode, as well as links to any of the resources, websites, or books mentioned during this episode. And don't forget to check our upcoming live webinar for this month at engineeringmanagementinstitute.org. Additionally, for those engineers struggling with unemployment or uncertain about how to make a career transition, I have created some free training resources with an opportunity to join a more intensive program called the Engineering Career Accelerator. You can find more information at engineeringcareeraccelerator.com. Until next time, I wish you the very best in all your engineering endeavors.